Okay, in this video, I want to just go through surface integrals and review all the different contexts in which we've seen those in chapter 16. So a basic surface integral would just be the double integral over S of f of x, y, z ds. Here, S is the name of the surface. This capital S means we're integrating with respect to surface area. Okay. All right, and what I need to do to evaluate something like this is parameterize the surface. As you can see, this is a double integral, but my integrand is a function of 3 variables. Beauty of parameterization is it matches the number of variables to the dimension of the object. Okay. Now, I have two common options for how I would do that. If I parameterize using R of uv over some region D, then this becomes the double integral over D of f of R of uv. Then I'm going to have my scaling factor dA. Notice when I'm integrating over the surface, I'm integrating with respect to surface area. When I'm integrating over the domain of my parameterization, I'm integrating with respect to flat area, dA, in the parameter plane. Okay. And that scaling factor is just the magnitude of del R del U crossed with del R del V. Okay. Now, that's for a generic parameterization. That's actually all I need to know, because I can always parameterize my surface. But if I had that z was a function, oops, let's not use f, let's say z was a function g of xy, and my surface was the graph of this function. S equals the graph of g over some domain D. If I have that, I can actually come up with a parameterization, so I could do this. The parameterization would just be R of uv equals, let u be x, let v be y, and then z is just a function, of u and v. But this one is so common that I hope you've derived what this is enough times that you've accidentally memorized the result. And you can go ahead and use that result if you have, that you're going to get the double integral over D of f of xy, g of xy, so you'd have to express your z in terms of the other 2 variables because they're essentially becoming your parameters. And then the magnitude of this cross product is just 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared, and then we're integrating that with respect to area in the xy plane. Okay. Now, this generalizes, of course. Right now I've written it with z being a function of x and y. That's the most common. But if I've got y as a function of z and x, or if I've got x as a function of y and z, it works just as well. I would simply, if I were writing out the parameterization, u and v would be whatever my 2 input variables were, and the third variable would be a function of those. Okay, so that's our basic surface integral. Now, the main example of a surface integral that we saw was a flux integral. So let's take a look at a flux integral. So flux, which can be noted with a capital phi, would be if I have a vector field and I'm integrating f dotted with n ds over that surface. Okay. So I'm basically integrating the component of that vector field that's normal to the surface. And not that's a little bit of a misnomer. I'm not integrating that component because that would still be a vector. I'm integrating the signed magnitude of that component. Okay. Now, of course, the way I would evaluate this is by parameterizing things. So, if S is parameterized as R of uv over d, this just becomes the double integral over d of f of R of uv dotted with, now the principal unit normal vector, if I've parameterized things, is simply going to be plus or minus del R del U crossed with del R del V normalized. And then I get my scaling factor, which is the magnitude of del R del U crossed with del R del V, and we're integrating dA. And of course, that scaling factor cancels. So this is very similar to our main example of a line integral, which was a work integral. The scaling factor that we have in switching from, in that case, d little s, integrating with respect to arc length, to integrating with respect to our parameter dt, that scaling factor canceled with the unit tangent vector. Here, the scaling factor cancels with the unit normal vector. And so I end up with just the double integral over d of f of R of uv dotted with plus or minus del R del U crossed with del R del V dA, where that would be area in the UV plane. Now, quick note on this plus or minus. You don't see that in the textbook. The textbook supposes that you use a parameterization that comes with the proper orientation. We're always working with an oriented surface, and I can find a parameterization that will give me the right orientation. However, in practice, I very often look at a surface and say, oh, I know a parameterization. I'm going to just pick the parameterization that I know. And then I have a 50-50 chance that it gives me the right orientation. If it does, I use the cross product of the partials. If it doesn't, I use the opposite. So I'm just going to make a note here. This is determined by the orientation. And so you need to check. If you know that you've got a surface and it was oriented out, pick a point, find what this vector is. If it's pointing out, that gives you the correct orientation. If it's not, it doesn't. Okay, excellent. So we get this. Now, once again, there's a nifty shortcut. If S is the graph of z equaling f of xy, and this can be modified if x is a function of the other two variables or if y is a function of the other two variables. If that's the case, again, we could just write a parameterization, letting u be x and v be y, and then z would become a function of u and v. But that's such a common situation that hopefully you've worked it out enough times that you've accidentally memorized the result. And in that case, we get the double integral over d of f of, that would become x, y. Oh, I can use f here because I'm not using it for anything else. F of x, y, dotted with plus or minus, and then there's a 1 here. If there's a 1 here, it's the opposite of the partial of f with respect to x and the opposite of the partial of f with respect to y here. Obviously, if I took the opposite of this, this would become a negative 1, and I would not write the negative sign in front of those two partial derivatives. Okay. And again, the plus or minus is going to be determined by the orientation. What's really nice about this is that's upward, because the z component of my non-normalized normal vector is positive. If I took the opposite of this vector, I'd have a negative 1 here. Very clear to see that that's downward. Okay. So this makes it very quick to check what orientation I want and to pick the correct one. Okay, so that's evaluating flux, which is the main example that we had for a surface integral. Now, the big theorem that we have for that one is the divergence theorem. What I'm going to do, because this video has been going for a little while, is I'm going to stop this video here. The next video will pick up still talking about surface integrals and just talk about the divergence theorem and when that can be used, and probably just as important, when that can't be used to evaluate a surface integral.